All right, so the other day we were talking a little bit about how to find the area in a plane, and so we had functions that look like this. Maybe we had a function here and a function here, and we integrated from, say, A to B, and we found the area maybe enclosed in the region or something like that between the two functions. So the next step is to figure out if we can use a similar procedure to find the volume of different geometric shapes that are described um, by some set of functions. So let's take a shape that looks like this, sort of a rectangular pyramid. So it looks a little bit like that. And if we uh, if we were to take a cross section of any piece of this solid, then we might find that all of the cross sections look like squares of different sizes. And so we could determine the volume of this shape by um, figuring out a way to relate the cross section to its position on the x-axis. So maybe the x-axis goes through the center of all of these squares, and the for this figure, let's say that the side length of this square is given by where we are on the x-axis. So if we're at um, A on the x-axis here, then the side lengths are A and A. And if we're at some other value B on the x-axis, then the side lengths of the cross-sectional slice are B and B. So we might be able to say then that the area of each cross-sectional slice as a function of our position on the x-axis is given by x squared, since wherever we are on the x-axis, the side length of this square is the same as that position. And we can see if we're at 0 on the x-axis, we're at a point, so we don't really have a cross-section. And if we're at some value here, then we do have a square, and it's going to have that same side length. Um, so we can use the idea of an integral to create a volume. So if I want the volume of the shape, then all I need to do is sum all of these areas, all these cross-sectional areas together, like stacks of sheets of paper, until I have the entire volume. Um, and remember that one of the ideas of integration is sort of doing that sum. So let's say that we want to go from 0 to x equals 3. So those are going to be our bounds. And so the volume is going to be equal to 0 to 3, our function of the area of the cross-sectional slices with respect to dx. And if we sum all of these cross-sectional areas together from 0 to 3, then we'll have made the volume of the solid by adding together all of the infinitesimal little bits of area. And the dx, we could think of the dx as being, let me take one of these cross sections here. So here we have x, and this is the area And we could make our infinitesimally small bit of volume by giving it a thickness, and the thickness is dx. So the volume of this piece is, in this case, x squared dx, and so we're using the integral to sum all of those little pieces together between 0 and 3. So with that, we can carry out the integral. So we'll go from 0 to 3 of x squared dx. Integrate that, and we'll get x cubed over 3, evaluated from 0 to 3. And so the volume of this square-based pyramid is 9. And if we were given units, we could provide the units. So we could say, since we don't know what the units are, we could just say units cubed as sort of a generic way of providing units for our answer. So sometimes it's easy for us to use an integral to find the volume of a solid if we can easily relate the cross sections of the solid to our position along an axis. And that's what this is an example of. Sometimes sometimes we can find the volume by rotation. So let me show you what I mean. Let's say that we have a object that looks like this, sort of like a trumpet bell. So it kind of looks like that. And then over on this side looks similar. So let's say that that's our, let me make this a little bit more symmetric. Looks a little bit better. There we go. So that's our shape, kind of like this section of a trumpet bell. And so in this case, if we were to take cross sections, we might see that each of our cross sections is a circle. And so we could use the same argument as before to construct this this shape. And so we might say that the radius of each of these circles is some function with respect to the x-axis, and so the area of the circle would be given by pi r squared, so we'd have pi, and then we would square this function that's giving us the radius with respect to the x-axis. And if we wanted the small bit of volume, which let's call dv, if we wanted the little bit of volume of each of the shapes, so here's our radius, then we would need a thickness, and we could think of that as a small slice of a cylinder, and so it would have the thickness dx. So we would have the area as a function of x times dx, and we can use an integral to put those all together. So very similar argument as the last example. Another way to think about this, which comes in handy for more complicated shapes, is that in reality, the thing that's going to give us the radius is this function here, whatever this function is. So let's say that that function is maybe just let's say it's x squared plus 1. So this curve here is given by a piece of a parabola. So another way to think about building this shape is to rotate that curve around the x-axis so that it makes, or to rotate this area, this planar area here, around the x-axis so that it makes that shape. And if we wanted to do that, the equation would come out very similar. It would come out the same. So we can think of all these circular cross-sectional slices. In this case, the function giving us our radius for the circle is actually x squared plus 1. So we can integrate this. And let's say that our bounds in this case are going to be from 1 to 4. And so we could integrate from 1 to 4. The volume is going to be given by the integral from 1 to 4 of our infinitesimal bit of volume, which is our area. So pi r squared. In this case, r is given by, the radius is given by the height above the axis to this curve, and that's this function here, that's x squared plus 1 squared times dx. And so then we can evaluate that function. So we'll have v equals the integral from 1 to 4 of pi. We're going to need to expand this, so we're going to have x to the 4th plus 2x squared plus 1 dx. And then we can integrate that. We get pi times x to the 5th over 5 plus 2/3 x to the 3rd plus x from 1 to 4. And then we could evaluate that.